Hello, everyone. Welcome back. We are to the last section in Chapter 8. We're going to be testing a claim about a standard deviation or a variance. Just to remind us, that means we are testing sigma, which is the population standard deviation, and the variance is the same except it's sigma squared. We talked about that in Chapter 7 a little bit. This one is a little bit different, which is why I made a separate video for this. We have to do a lot of stuff manually, and I want to point out for this video, you may need to pause it. You will need a chi-squared distribution table of some sort. Either your teacher provides that for you, or you can just find it on the internet. Just type in chi-squared distribution table, and thousands will come up. But we will get to that. But make sure you have that handy as you're going through this video. All right. What makes this one different is that we have to do everything manually. Our test statistic if you go back to section 8.1 is here. And there's no program or test that we can run in our calculator that does this for us unless you've pre-programmed yours to do it. So we will be using this formula. We'll also be using the table. And remember that a chi-squared distribution does not look like a T or a Z distribution. It's not bell-shaped. It is skewed right with a longer tail to the right, which we'll see in just a moment. So let us begin this. And there's a lot of components to this. So let's take our time. Over the years, the restaurant Zoodle has had a mean customer satisfaction rating of 71 for its deliveries, with a variance of 52. The price for delivery was recently changed, which the owner claims has caused the variance to change. So we already have some moving parts here. We are testing the variance, which is 52. And they are saying that some of the changes are going to make the variance change. Please note that this is going to be a two-tailed, which is going to cause us a few more issues than we'd like to deal with, but we have to. Let's continue on. He phones a random sample of 24 customers, so let's write that down. N is 24, which means our degrees of freedom is 23. 24 customers who ordered deliveries at the new price and asked them to rate their satisfaction. The customers in the sample have a mean rating of 72 with a variance of 18. We don't need the mean for this one. It's not part of the formula. Assume that the customer ratings for the newly priced deliveries are approximately normally distributed. Is there significant evidence at the 1% level to conclude the owner's claim is correct? Okay, so first of all, we are using a chi-squared distribution, which I believe is written out in ALEKS like that. And before we find the value of the test statistic, let's draw a picture to get a good idea of what it is that we're even looking at. So this is a chi-squared distribution. Remember, that one starts at 0. And this is a two-tail. And this value here is going to be half of our 1%. So this is 0.005. And this one here half a percent. And we need to find chi-squared left and chi-squared right. Now, to do that, I'm going to have to use my table. Now, I want to point out that in the middle here, that's 99%. And what that means is the area to the right. Let me point this out real quick. I want to show you in our table, and I know the print is very small, but this is going to talk about area to the right of the critical value. We can see that there. We'll come back to that. All right, so clearly the area to the right here, off to infinity, is 0.99 plus 0.005, which is 0.995, again, with the degrees of freedom of 23. So let's find that first value. So degrees of freedom is 23, area to the right is 0.995. So 0.995, 23, there it is, 9.260. Area to the right here of this one is just 0.005. So now we are at 23. And now we're way over here at 0.005. So we are at 44.181. So 44.181. All right. So we have our information. Let's find the test statistic. Chi-squared equals n minus 1, which is 23. So we're using this formula up here. Chi-squared equals n minus 1 s squared over sigma squared. So 23 times s squared, which is 18, over sigma squared, which is 52. Notice they're already squared, so we don't need to square them. So let's see what we get. So we were getting 23 times 18 divided by 52. So this means our test statistic is 7.9615. Okay, I'm going to note that that is right there. We are in the critical region. I want to talk about the p-value a little bit, though, and this is where things get a little tricky. So let's talk p-value. The p-value, so let's start here. If s, or s squared, is less than sigma, which it is in this case, then it's in the left tail. Meaning it'll be the area of the left tail, the p-value in the left tail. If s, or s squared, is bigger than sigma squared, or sigma squared, then it's right-tailed. Now we can see that the 18 is less than the 52 here. So this is definitely in the left tail, and we can see the left tail. And to be clear, our p-value is this area here. So this means that when we're looking for the p-value, it's going to be chi-squared CDF, and this is going to be 0 to the test statistic. If it's in the right tail, then it's going to be chi-squared is CDF, the test statistic, to infinity, meaning 9999999. Okay, and here's the thing with a two-tail that is going to really mess us up is when we find, in this case, I'm going to find the left tail value. So for this one, the p-value, and I'm going to even say that this is actually going to be half of the p-value, is going to be in chi-squared CDF from 0 to 7.9615. So to find the full p-value, after I do this, I'm going to have to double that. Chi-squared CDF. This one does start at 0. If it doesn't, you have to start at the tested. If it's right-tailed, then you have to do the test statistic, comma 99999. This one works out for us, 7.9615. Oh, I forgot the degrees of freedom, comma. Degrees of freedom, which in this case is 23, if I remember right. 23. 3. And there we are. Remember, this is half. So the full p-value, I'm going to have to double that, right? Times 2 is about times 2, 0.00313. And I'm going to notice that that is definitely less than my alpha. Now, this particular problem doesn't ask for the p-value, but you will have homework questions that do. And if it's two-tail, you'll have to remember to double that when you do that. And you'll need to know, is it left tail or right tail? As you're looking at this, as the chi-squared CDF will change because of that. All right, so the test statistic we have found, let's write that out. That is chi-squared is about 7.9615. This one's asking for the critical values, not the p-value, but again, some of the problems you will need to know what the p-value is. Critical values are 9.260 and 44.181. And because the p-value is less than our alpha, and at the same time our test statistic is in the critical region, we are going to reject the null hypothesis. So can we claim that the variance is not equal to that? Yes, we can. Now there's a lot going on with this one. Let's see if I can get it all on one screen there for us. A lot going on. So once again, with the test statistic, we have to do that manually. For the p-value, if the sample standard deviation is less than the population standard deviation, S is less than sigma, then we're in the left tail, and the p-value is going to be chi-squared CDF from 0 to the test statistic. If it's the other way, if the sample standard deviation is bigger than the population standard deviations, S is bigger than sigma, then we're in coming up with the right tail, and that's going to be chi-squared CDF from the test statistic off to infinity, which to us means a really large number, 9999999, whatever. If it's two-tail, then when we find that p-value, it's actually only half the p-value. We have to remember to double that. If it's not a two-tail, then we don't need to do the doubling. Let's do our last problem. All right. With its old software, a robot in an evaporator assembly line applied a mean of 3.2 milliliters of lubricant per evaporator with a standard deviation of 0.69. So that is our, and notice we're talking about standard deviation, so that's just sigma, not sigma squared. The lead engineer thinks that following a recent software update, the standard deviation is now less than 0.69. So there is our alternative. To see if this is the case, he tests a random sample of 15 evaporators that were assembled following the update. He finds that for the evaporators in the sample, the robot applied a mean of 3.1 milliliters, which we don't need, of lubricant per evaporator with a standard deviation of 0.42. There's our S. Is there enough evidence to support the engineer's claim at the 1% level of significance? Okay, so here we go. Let's do our picture. This is chi squared. This is 0. And this is a left tail test. So we don't have to worry about doubling our p-value. And I'm going to notice that the sample standard deviation, the 0.42, is less than sigma. So we are indeed in the left tail when we get our test statistic. All right, once again, this is going to be a chi-squared test. And again, they write it out chi-squared. So we need to find our test statistic. So our test statistic, which is chi-squared, is n minus 1, which is 14. Oh, I didn't find the critical value yet. Let's do that. So this area here is our 1%, which means area to the right is 0.99. So degrees of freedom was 14.99. Let's get our table. All right, so once again, our degrees of freedom is at 14 and 0.99. So 14 and 0.99. So we're looking at 4.660. So let's go back. All right. So let's find our test statistic. That is, let's see, I'll write the formula up for us real quick. So our test statistic is n minus 1 s squared, or sigma squared. N minus 1 is 14. S is 0.42. In this case, I have to square it because we're dealing with standard deviations. Over 0.69 squared. Let's see what we get. So we're getting 5.187, which I'm going to notice is not in our critical region. I'm also going to find the p-value. Now notice that, and again, the p-value is this area here, all of that area. And you'll note I'm in the left tail because 0.42 is less than 0.69. So this is going to be chi-squared CDF from 0 to 5.187. It's a comma. Again, this one does start at 0 also. However, if it doesn't, you would have to start at the test statistic and go off to positive infinity, which is the 99999. But that doesn't apply to either of these cases. And we need our degrees of freedom, which is 14. And so our p-value in this case is 0.01696, which I can see is a little bigger than our alpha. So and let's see what they're asking for over here. So they want the test statistic, which is our 5.187, our p-value, which is 0.01696, which means our conclusion is that we are going to fail to reject the null hypothesis, which means we're sticking with the null hypothesis. So can we say that it's less than the 0.69? No, we cannot conclude that because we are failing to reject the null hypothesis. I hope you found this helpful.